Hello, algebra. So today we are looking at radicals and rational exponents. So first things first, I want you to take a minute, sketch a square with each of the given lengths. All right, so I'm going to skip over here to a square. Right, remember a square has to have the same numbers on each side. So I'm going to do 1, 2, 3, 4. My lines are not perfectly even. That's okay. Hopefully your artist out there can, do a little better than me. The length of 5, I've got 1, 2, 3, 4, 5. I've got 5 strips, but I need to have squares. So 1, 2, 3, 4. So that's 1, 2, 3, 4, 5. So I've got a 5, right? There are 5 boxes on the side, and there are 5 boxes on the top or on the bottom. So that's a 5 by a 5, right? So sketch out the square, determine the areas. Well, if I count each of these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, you can see that my area is going to be 25, right? I counted the boxes. Another way of doing that would be 5 times 5, which is 5 squared. That's why we use that squared term for the 2 exponent, right? So now, what would you do to determine the length of each side if you were given the area? So let's say you were given an area of 36. What is the length? That is our question. What is the length? Well, obviously, we could take all of our little boxes and we would arrange them until we got them perfectly into a square, right? Where it was even. Now, I could make it so that it was a 3 by 11, or 12, excuse me, by 12, that would get 36, but that is not a square. So this does not work because it has to be a square. All right, it has to be a square. So that means I would need a 6 by a 6. That would have an area of 6. So what's the length? 6. Another way of taking that would be to take the square root of 36, right? And we know that that's really 6 times 6. So that is 6. So area for 49, same idea, right? What number times itself equals 49? Or x squared equals 49. If we square root both sides, then we get an x equals 7. Same idea. I know you guys can do it with these ones as well. So I'm going to post this. You should have access to it in my notes as well. I would keep this in a very handy spot where you can reference it easily, because this is our squared table, this is our cubed table, and this is the fourth table to the 4th power. Remember, 1 to any power is always 1. You can have an infinite number of 1s, right? 1 to the 100th power, it's still 1. And I'm going to add to this 1 to the 0, because we know anything to the 0 is always 1. Even 1 to the 0, it's 1. All right, so I just wanted to remind you of that. In fact, if we did a 0 table here, we could do 1 to the 0, 2 to the 0, it's always 1, 3 to the 0, 4 to the 0. So let's take a look at some radicals. That's what this square root is called. And radicals can come in many different kinds of powers. So we could be looking at a square root. It's got a little invisible 2 here. We could be looking at a cubed root. We could be looking at a quad root. There are many different kinds. So roots can go forever, honestly. So if we have a square root, or a radical in this case, some number n. Again, if you see just a square root, like the square root of 4, for example, that means that you are taking the second root of 4. So there is an invisible 2. It's the one time 2 is a ninja. Never happens otherwise. We can rewrite this radical as a fractional exponent. Pretty cool, right? So we can turn it from an nth root a into a to the 1 over n. All right? So it moves to the denominator of the exponent, Well, let's just say that we had a that was being raised to some power. So I'm just making a to a power. That's all I'm doing. I can rewrite that so that I still have my nth root of a, and it's being raised to an m power. Now here's what's really, really cool. I know that this is really a to the 1 over n to the mth, right? I just rewrote it That's all I did. I just rewrote it using our radical rule as a fractional exponent, rational exponent. And then I am going to do my product of a power of a product, power of powers really, and I'm going to multiply those out. So this would be a to the 1 over n times m over 1. So I'm really multiplying my numerators and denominators of the exponent, so that means I get m over n. Now, I would grab a color to help your brain. So here's my n's all over the place, and everywhere I see an n, I'm just highlighting it as orange. I'm going to do the same thing with my m's. So here's my m in purple. So hopefully that helps your brain. So this is pretty cool, right? And we know that the square root of 4 is 2. So we can use these rational exponents, the fractions, to simplify. So we have 125 to the 1/3. We want to simplify this expression. Well, you'll notice, this is why it's handy, you'll notice that there's 125 on here, and it's right there, right? This is really 5 to the 3rd power to the 1/3, all right? Now, if you like it better so that you have our 3 here is the 3rd root of 125, that works too. In fact, I'm going to do it this way first because I think that might be a little easier on your brain. So it's the cubed root of 125. Well, 125 is really 5 times 5 times 5. It's 3 5s, right? And it's the cubed root. Make sure you write that 3 there. Don't forget it. Otherwise, it turns into a square root. It's not a square root. It's a cubed root. It makes a difference. This 3 acts like a guard at a prison. All right? Our radicals are prisons. The 3 is the guard. So if we want to have a jailbreak or prison break or whatever, we need to have that exact quantity of our radicand, whatever's in here. So we need 3 of a number for that number to escape one time. Well, there are 3 5s, so they can escape once. So this would be just 5. So I want to show you another way of doing it, which would be using our exponent rules. So 5 to the 3rd power. I'm going to do my product or power of powers rule, excuse me. So I get 3 times 1/3. So that would be 5 to the 3 over 3, which is really 5 to the 1. So that's just 5. You'll notice it leads to the same answer. They are both valid ways of doing it. All right, they are both valid ways of doing it. This is option 1, and this is option 2. So I want to do this one down here with you. I am going to use this way of doing it. So this is a square root of 121, and then this is plus the 4th root of 256. So I'm going to look for 256 in my table up here. There it is, 256. So this is really 4 times 4 times 4 times 4, and it's the 4th root. And then 121, I only see right here. It's 11 squared. 11 times 11. So I know that I've got 2 11s. They can make a jailbreak, so I'm going to be left with 11. And nothing is inside prison, so the prison... For this one, I know 4 is going to escape one time. So I'm going to have a 4. So 11 plus 4 gets us 15. All right, I want you guys to try these 2 on your own. Okay, try these 2 on your own. For this one, we're going to move that 4 out front. And so we're looking at the 4th root of, well, this is really 9 times 9. But you can rewrite 9s, because those are really 3 times 3 times 3 times 3. So the 9 could not escape. I need to have 4 of a number to escape. 9s cannot escape. But I have 4 3s, so the 3 can escape my jail. And then for this one, when we do the 6th root of 64 plus the 2nd root of 25, I know that the square root of 25 is 5. 64 is a little bit more challenging. 64 is a little bit more challenging. So I'm going to come up here. I want you to write this down. 2 to the 5th is 32. 2 to the 6th is 64. And 2 to the 7th is 128. So that will be helpful. I think it'll be helpful at least. And then I would say 2 to the 8th is 256. Do you have to memorize all those? No, but again, it's a nice handy reference chart, right? So if we want the 6th root of 64, 64 we know is 8 times 8, but we need 6 of a number. That's only 2 8s. That does not work. We also know 64 is 4 3s. I'm sorry, 3 4s. 3 4s does not get us 6 of a number. So we also know it is 6 2s. So 2 times 2 times 2 times 2 times 2 times 2. So that means we have 2 plus 5, because the 2's can escape, gets us 7. And I will box my answer so you can see it easier. All right, I'm going to turn the page. This is the last page of notes for this part of the lesson. So we want to simplify each expression here. Simplify each expression. So I would start by making it a radical, excuse me. So 216, this is your radicand, it's the inside. The radical is the outside. This is the root, right? The radical is the little boxy guy. And I'm going to leave my 2. The 2 stays out here. If it helps you to color code, please color code. So we have 216. I want the cubed root of 216. I'm going to give you a hint. Look in the cubed table, and you will see that for 216, we have 6 cubed. Now, the cubed root of 6 cubed, that means I've got 3 6s here that can escape, right? Because this is really 6 times 6 times 6. So that means I have 6, right? They can all escape. Hey, 6 squared is 36. So that's all we're doing with these. So I'll leave these ones up here for you to try, all right? I'm going to jump down here a little bit because this is a little bit more different because now we're looking at negatives. What do you do with a negative? We're going to look at it. Now, this is a negative 8, all right? It's a negative 8. So that negative, we want 3 of the same number that makes negative 8. Well, 8 I know is really 2 times 2 times 2. Right? But there's a negative here. So this is really negative 2 times negative 2 times negative 2. Does that really make negative 8? Well, negative times negative is a positive times another negative is a negative. So yes, it works. So that means that negative 2 is going to escape. And then I want to square it. Well, negative 2 times negative 2 is the 4. This is why it matters. That 2 is touching the negative as well. Okay? So it's negative 2 times negative 2, which gets us a positive 4. It gets us a positive 4. So let's do that with this one now, because this one's different, very different. So this one has a negative cubed root of 8 to the 4th power. That negative is not included. Okay, this one is included. This one is not included. So that means I want the cubed root of 8. Well, that's really 2 times 2 times 2. So the cubed root of 8 is just going to be 2. This was not included in that, right? So it's going to be negative 2 to the 4th power. Well, that's negative 2 times negative 2 times negative 2 times negative 2. Negative times negative is a positive. So our negatives cancel each other out, so to speak, right? Negative 2 times negative 2 times negative 2 times negative 2. So that makes a positive 4. That makes a positive 4. 4 times 4 is 16. So I want you to try using your negatives for this one, okay? I do want to make a quick note that some of you might say, well, if you have a 4th power, doesn't that make it a positive? Because if you have negative 3, let's just say squared, that would be positive 9. Same thing with 3 squared, that's a positive 9. You're right. When you have a negative and you square it or you raise it to an even power, then you don't know if it was a negative or a positive. So sometimes you'll see people, for example, for like the square root of 9, you'll see it written as plus or minus 3 because we aren't sure if it was a positive 3 or a negative 3. So I wanted to make that note that you will see that. We're not going to deal with it much this year, but you will see it especially in math. And that's because positive 3 squared could be a positive 9 or negative 3 squared could be a positive 9. And this only applies when you have an even exponent. So quick note, more notes in the next section, which is still 6.2.